Good day everyone. We would like to present our digital logic project, which is designed and simulated using this software. Our project is about smart door lock system, which demonstrates how digital logic and sequential circuit can be applied to a real security application by using a password mechanism to control access. So for our background, digital and electronic systems play an important role in modern security applications such as hotel, office, and residential buildings. Traditional mechanical lock rely on physical keys which can be lost or easily duplicated, that leading to potential security risks. Thus, to overcome this limitation, smart door lock systems are introduced to improve both security and user convenience through digital authentication. This system performs password verification, access authorization, and security monitoring. By using digital logic circuit, user inputs can be verified based on predefined conditions, and an alarm mechanism can be implemented to detect multiple incorrect attempts and prevent unauthorized access.
So now, let's move on to the problem statement part. For our problem statement is, a hotel visitor wants to use a smart door lock system to access their assigned room. The visitor is required to enter a 3-bit password to unlock the door. When the enter password matches the store password, the door will unlock and the green indicator light will turn on. The door will then lock back automatically when the visitor closes the door. Next is the suggested solution. To solve the problems, we have designed a smart door lock system using digital logic circuits, and then the system uses a 3-bit password verification to ensure that only authorized user can unlock the door. When the correct password is entered, the door unlocks and the green LED lights will light up. If the password is incorrect, a counter will record the failed attempts and the red LED lights will blinking as a warning. After 3 incorrect attempts, an alarm is triggered, and the red LED lights will also remain on. Once the correct password is entered, the counter will reset automatically, and the system returns to normal operation.
Next, I would like to present the system requirement for our smart door lock system. For functional requirements, the system accepts 3-bit password input from the users. When the enter password matches the store password, the system unlocks the door and the green LED turns on to indicate successful authentication. And if the password is incorrect, the system increases the wrong attempt counter and the red LED blinks to indicate access denial. After 3 consecutive incorrect password attempts, the system triggers an alarm and the red LED remains on continuously. When the correct password is entered, the system is able to reset the counter automatically. In addition, after the door is closed, the system automatically locks the door again to maintain security. Next, this slide is about the hardware and logic requirements of the system. 3 toggle switches are used to enter the 3-bit password, which is labeled as P2, P1, and P0. And a push button is used as the enter signal to confirm the password input. Next, flip-flops are used to implement the counter to store the system states. And basic logic gates such as AND or XNOR and NOT gates are applied to construct the comparator and control logics. LEDs are used to indicate whether the enter password is correct or incorrect, and an alarm indicator is included to signal the security breach. So the entire system is designed and simulated using this software.
For this section, I will explain the system implementation for our smart door lock system. First, the system uses a comparator to compare the enter password with the store password. The overall operation of the system is controlled by a finite state machine, or we can call FSM, which manages the lock machine, indicator light, and alarm. Initially, the system starts in a locked state. When the correct password is entered, the door will unlock and the green light will turn on. If a wrong password is entered, the system will implement attempt counter and the red light will blink to indicate an error. After 3 wrong attempts, the system enters the alarm state, where the alarm and the red light remain on until the system is reset. Next, in this slide shows the state table of our FSM. So for the input signal, E represents the enter button, P represents whether the password is correct, C is the attempt counter, D is the door sensor, T controls the blinking behavior, and R is the reset signal. For the output signal, L controls the lock, G is control the green light, R is control the red light, and A is control the alarm. The FSM stack is encoded using Q2, Q1, and Q0 starting from the IDLE state. From the IDLE state, when the enter button is pressed, the system moves to the check state to verify the password. If the password is correct, the system transitions to the unlock state and activated the green light. If the password is wrong, the system goes to wrong state and increment the counter. When the counter reaches the third wrong attempt, the FSM transitions to the alarm state. In the alarm state, the alarm and red light stay on until the reset signal is activated, which returns to the IDLE state and reset the counter. The slide shows the state diagram that visually represents the FSM behavior. The system starts at S0, which the IDLE or lock state. When the enter button is pressed, the FSM transitions to S1, which is check state. If the password is correct, the system moves to S2, the unlock state, where the green light turns on and the door is unlocked. Once the door is closed, the FSM returns back to IDLE state. If the password is incorrect, the FSM moves to S3, the wrong state, where the red light blinks and the counter increases. After 3 wrong attempts, the system enters S4, the alarm state, where the alarm and red light remains on. The system only can exit the alarm state where the reset button is pressed, which brings the system back to IDLE state.
So now let's move on to the password verification logic circuit. The system uses a 3-bit password represented by the input switch P2, P1, and P0. These switches allow the user to enter a binary password. The correct password is stored internally using fixed logic values. Each enter password bit is compared with the store password bit using XNOR gate. An XNOR gate outputs a logic high when both inputs are the same. The outputs of all XNOR gates are connected to a 3-input AND gate. This AND gate produces a signal called password match. When password match is high, all bits match, and the door unlock signal is activated. When it is low, the password is incorrect and access is denied. This signal is also used to control the counter and alarm logic in the system.
This slide shows the password comparator circuit, which is responsible for verifying the user's enter password. P0 to P2 inputs indicate the user enter password, while K0 to K2 inputs indicate the store password. Each bit of the enter password is compared with the corresponding store password bit using XNOR gates. If both bits are the same, the XNOR output is logic high. All XNOR outputs are then combined using an AND gate to generate a match signal. The match signal is further controlled by the enter button to ensure the password verification only occurs when the user confirms the input. If the password match, a correct signal is generated and sent to the controller. Otherwise, a wrong signal is produced, it will increment the wrong attempt counter. This comparator design ensures the matching of password verification before any state transitions occurs.
I will be explaining about counters. In our system, we use synchronous counter using D flip-flops. It counts wrong password attempts only. Counter increments when enter equals to 1 and wrong password equals to 1. The maximum count is 3 attempts. Counter stops changing state after reaching maximum value. Alarm condition is pledged until reset. In counters, we have clock and control logic. Clock is gated with enter signals. Flip-flops update only when enter is pressed. It is to prevent unintended state changes. Enter must be pressed for 1 second to ensure stable input and accurate counting. Next, there is reset function. Reset and door closing returns all flip-flops to initial state. Alarm is cleared and system is ready for a new session. In counters, we also have unlock operation. Unlock is activated when correct password is entered and system is not in alarm state. Green LED turns on and door unlocks successfully. We also have alarm operation. Alarm triggers after 3 consecutive wrong attempts. System ignores all inputs after alarm is on. Alarm remains on until reset. These are the Boolean expression in our counters. This is the counter circuits. And this is our combinational system circuit.
In conclusion, the smart door lock system was successfully designed by using digital logic concept. Password verification was implemented using a comparator to ensure correct access. The overall system operation was managed by finite state machine, which coordinate the lock machine, indicator light, and alarm. The inclusion of wrong attempt counter and alarm machine enhanced the security of system. This project demonstrates the practical and real-life application of digital logic in access control system. Through this project, we gain a deeper understanding of sequential logic design and finite state machine. We also learn how to use stick simulation software to visualize the system behavior and to test the operation of the circuit efficiently. During the development process, we faced challenge in integrating multiple system components such as wrong attempt detector, alarm activation, and reset control. This challenge will overcome through critical thinking and problem-solving skill. Overall, this project provides valuable hands-on experience and helps us apply theoretical digital logic concept to practical and real-world application.